Hello guys, welcome to this video. So in this video, I'll be discussing a very interesting question, and some of you definitely have. I recently released a poll about which of the video would you most like to see, and some of you definitely wanted to do a video on this topic. So as you can see on the title, the video is like how not to hate physics. Start with I could have said how to love physics, but I didn't say that. I said instead how not to hate physics because see love is something irrational, and what you love and or not, that is up to you. Like, for instance, if you were taught physics the right way, maybe you would have developed a love for physics, and maybe there's something about the kind of stuff you read when you grow up, the kind of environment you grow up in, even some genetics might play a role. So similarly, if you can love biology. So I can't say that physics is better than biology. Loving physics is better than loving biology. Such kind of statements make no sense. Like, what you love is up to you. There's no wrong or right choice. But hating a subject is not correct unless you have some strong logic in doing so. So although you might not love physics, that's up to you. But you shouldn't hate physics, because if you do, then you have to show some logic. So in this video, I'll be discussing some logic, some counter logic, like why physics is not a hateful subject, why you should not hate physics, even if you might not love it. Whether you love physics or not, that's up to you. But I will at least show you, tell you, like, why physics is not a subject to be hated, why it's extremely interesting. So that's why I named the video how not to hate physics and not how to love physics. So yeah, okay, so consider my case. I'll just, I think I discussed this in a previous LinkedIn post or somewhat, but somewhere anyway. Anyway, let me just discuss it like in short. So, yeah, like today physics, I am a physics undergraduate. I write articles on physics and so on and so forth. So today physics is a big part of my life, but I was not initially interested in physics, to be honest, uh, like, uh, like when I was in school, maybe in class 7 or 8, from 7 or 8, you get a taste of what physics is like. I mean, not a taste actually, just a very little idea, right? Because before 7, what you do, that's not physics. That's not just very basic. Like, that's nothing. And even in 7, 8, you don't get a taste of real physics. But yeah, there you just learn a bit of stuff like, optics, and optics means the very basic ones, the ray optics, obviously the basics of ray optics, and this magnetism and sort of stuff. And yeah. So anyway, and then you have this the basic stuff like the mirror formula, like reflection, refraction. Then in class 10 you have the mirror formula, and then in class 9 you have a bit of mechanics, acceleration. I'm just talking about the Indian education system, okay? The acceleration, and the three equations of motions, Newton's laws of motions, gravitation. So the thing is that, like, when I was in those classes, I didn't like physics very much. Like, yeah, I did well in my physics and physics exams, and even in math exams. But yeah, I didn't have any particular love for physics or math. And well, I could understand what was being taught to me, and in some cases I couldn't understand easily. But after a bit of thinking or after a bit of help from my teacher, I could understand. Like, and I did pretty well in my exams. But I just didn't care, like, whether a braking car would stop after 10 seconds, like those kind of sums you're asked to solve in mechanics, and or an image should be formed 20 centimeters from the mirror. That's kind of sums you are asked to solve in optics, or whatever, like these kind of examples. Because it seemed to me at that time like these were just trivial. Like, yeah, like, okay, so there are some formulas: 1 by f equals 1 by v plus 1 by u. Then u equals half, s equals ut plus half at square and all this. But okay, I just thought, okay, these are the formulas, these are the basic mathematical ways to derive them, and using these formulas, these are given. So using the formula, you can find out this quantity, and then that's the answer. But okay, that's all right, that makes sense. And yeah, that's even somewhat wonderful, like you can predict all these things. But it didn't surprise me or interest me that much, because at the time I was too caught up in neuroscience and consciousness. I was mainly inspired interested in consciousness, because that was a very the main reason I think is that consciousness is not taught in high school. Even neuroscience is not taught, just the basics of neurons and the nervous system. But yeah, consciousness is definitely not taught in high school. So I could explore consciousness my way. I could just, go to the internet and read interesting articles on consciousness, buy some books on consciousness, and I could explore it in my own way. And that is, I think, the main factor responsible, that was responsible for developing my interest in consciousness. Physics, I could have explored in my own way. There are a lot of interesting stuff about physics to read on the internet. There are a lot of interesting popular science books on physics. But the way physics was taught in the school, that really didn't push me to explore the subject further. And I think that is the case for most high school students, I think. And that's one of the main reasons, like we don't develop an, like most people, or at least some people, don't develop an interest for physics, and they they eventually grow up to hate the subject. Like there is a general consensus among students that physics is really difficult, and like, yeah, I hate physics, I don't want to do physics, like who does physics, this kind of stuff. At least from my experience, from talking to high schoolers and even some college students, like even in my college, when I talk to students of other departments, like the first thing they ask me, like they which department are you from, and I say I'm from the physics department, and they're like, what, you're from the physics department, like why, what kind of people even study physics, like that's a very difficult subject, like, well, why do you study physics, what's there to be? And I was like, yeah, when I'm in the mood, I try to explain, I try like I try to tell them like why physics is so wonderful, and why physics is a fundamental science, and it's about the real world, it's about the ultimate truth. But in most cases, I just smile awkwardly and just walk off, like because it's I don't feel like explaining or doing all the explanation to these people, and I don't blame these people, it's not their fault actually. It's so yeah, the thing is that so at that point of time, I was, like I said, I was too obsessed with consciousness to admire physics and math. And yeah, in fact, if you were to tell my, say, 6, 7 years younger self that he will end up writing a book on physics, and like he would have laughed his head off. And but today, see, the situation is so much different. Today, physics is a big part of my life. So you never know what life has in store for you. So anyway, the point is that how did this change come about? I think it mainly came about the from like it all had to do with consciousness initially. Like I read a book called The Future of the Mind by Michio Kaku. So at that time I was looking for books on consciousness. I read a lot the usual David Eagleman books, The Brain, Incognito, and I read a couple of other books on consciousness and neuroscience as well. Then I thought like I just randomly came through this book called The Future of the Mind by Michio Kaku, and I just thought, okay, let me try this out. And it was extremely like very good book. It discusses a lot of future neurological technologies. Possibly it discusses a lot of neuroscience and consciousness. And the thing is that Michio Kaku is not a neuroscientist, unlike David Eagleman, and Michio Kaku is a physicist, and he discusses the concept of consciousness from a physics perspective. And obviously, since he's a physicist, he's writing, like there is a lot of physics involved. So that's where I first got interested in physics, because Michio Kaku's way of introducing the subject is, it's like as different as can be from the way physics is taught in high school. So yeah, this quantum mechanics, the notion of consciousness in quantum mechanics, this many words interpretation and all these things, this Eugene Wigner's interpretation, Schrodinger's cat, and the quantum nature of consciousness, this Roger Penrose's microtubules theory. Although most of this I'm talking about, these theories are probably not true, but still that was important to initially spark my curiosity in physics. And then I started exploring quantum physics, and a lot of interesting stuff. Of course, the basic qualitative aspects, because when I was like maybe 15 years old, I couldn't understand like all the deep mathematics of quantum mechanics. But I really got the interest, and I started exploring quantum physics and the philosophy of physics and the history of physics and this and that. And slowly, like unconsciously, I realized, like unconsciously, I started to shifting from consciousness to physics. And then one day I realized, like, no, I really want to do physics. That's more important to me. And then I started seriously reading about physics. Like it was no more popular science books. It was like, you know, dedicated courses, like of course free courses on Coursera, or maybe there are some really good material on YouTube as well. And then I asked my school teachers to teach me quantum mechanics. And when I was in class 10, like I was in like maybe 16 years old, and that time I really I'm really thankful to my teachers for that. Like they taught me the Schrodinger equation, and the quantum operators, and normalization, and like all the basic stuff you do in quantum mechanics. And then I, like I started writing about quantum stuff, and then I started but then I came up with a few original ideas and wrote a few research articles. And then I started to look for journals to publish my article, and then I found the YSJ, Young Scientist Journal, and then I joined them as an editor, and then I started writing scientific articles, and then I published a popular science book on physics, and so yeah, this is that. So most of you probably know that story, and even if you don't, that's not of relevance, that's not of importance here. So that's how I came into physics. But the thing is that to understand how why like how not to hate physics, we need to understand from where this hatred of physics comes from. So as I said, that's mainly because of the way it's taught. So whenever like usually what we do is that in high school or whatever, suppose let's take a very simple example: momentum. It's P equals mv. That's what momentum is, right? P equals mv. Momentum is mass times velocity. So when it's taught in high school, you just say that momentum is P equals mv. So this is the formula you have to remember. Now, if m and v are given to you, then you can calculate p, or like if any two of these three quantities are given, you can calculate the other. And students are like, okay, so this is the formula. Momentum is this product of mass times velocity, and then so I can solve the sums, and that's all. And so they just memorize the equation P equals mv, and then they do a few basic examples like the conservation of momentum and all those things, and that's done. So whenever you're doing physics, the first thing to do, so to not hate the subject, the first thing to do to develop an interest for physics. So to do that, of course, reading your textbooks will not. There is also a psychological factor here. Reading your textbooks will not help. So what I suggest is that if you really want to explore physics, like I'm not saying you have to take up physics, but you can just explore the subject, like just to make sure that this is like just explore it. And then if you think that no, this is not my cup of tea, fine, just leave it. But if you just want to explore it, I would say start from a young age, like from maybe 14 13 14-year old. You just start reading popular science books and physics, like readable books, Mishogaku, Neil deGrasse Tyson. Like there are a lot of books, Cosmos by Carl Sagan, the famous ones I'm talking about, Brief History of Time by Stephen Hawking, then Steven Weinberg. It depends actually. You start reading popular science books and physics because they discuss very interesting concepts in modern physics, like quantum mechanics, quantum gravity. Like these are very interesting concepts, and the way they're written, like you're like, okay, so physics is trying to uncover the ultimate secret of the nature. It really excites you. Okay, and so reading popular science books on physics will really get you interested in the subject. And in these popular science books, they don't deal with the topics like rigorously and using the mathematics, so it's easy to understand for even for 14-year-old 15-year-old kids. uh, the thing is that, so but if you really want to pursue physics, then you need to learn the mathematics, you need to have a formal training, you need to know the total history of physics. So for that, obviously, you need to like learn the usual textbook stuff. You need to do an undergraduate degree and then a master's degree and whatever. You need to do that textbook stuff. But once you have the basic interest of the subject, which can be developed by reading popular science or maybe even watching good YouTube videos, but once you develop that interest, then you will love to do it. But without that interest, you will not feel like doing it. So initially you do that, and then suppose once you have done that, when you are doing physics, my advice would be to, whenever you see an equation in physics, you ask yourself like, what is this equation telling me? Because there's a difference between physics and mathematics. Like mathematics, I shouldn't say mathematics in this context here, but anyway, the point is that like P equals mv, you're just memorizing the equation, that will not make me interested. You have to ask like, what is this equation actually telling me? Okay, so like I don't know if you have seen Oppenheimer or not. It's the famous movie by Christopher Nolan. I myself haven't watched the movie, but I watched that particular scene when like Oppenheimer was like, he went to Niels Bohr and he said that I don't want to do this experiments. I want to do like theoretical physics. And Niels Bohr says that then Oppenheimer says that my math is not that good. And of course, for theoretical physics, you need to be good in math. So then Niels Bohr says that algebra is like sheet music. The important thing is not can you read the music, it's can you hear the music. So can you hear the music, Robert? So the thing is that here reading the music corresponds to just memorizing the formula, like just like, okay, so P equals mv. But hearing the music means feeling the music. Hearing means, yeah, by reading the music you cannot really understand, like you cannot reading the music doesn't produce the same effect so that you get when listening to the music, like that same response, that same emotion. So the important thing is that you have to listen to the music. You have to ask yourself, what is this equation telling me? Because mathematics is abstract. Suppose if I tell you a mathematical formula, a plus b whole square equals a square plus 2ab plus b square, and if you ask what is this formula telling me, it's a foolish question, because this formula is not telling you anything about the nature of reality. It's a mathematical fact. Now, if you apply this formula into some particular real world application, the real world phenomena, and then if you define a to be this and the b to be that, then you can say that okay, this formula is telling, but the formula by itself, it's not telling you anything, like a plus b whole square equals or whatever, just any general mathematical formula, that's not telling you anything. That is the difference between maths and physics. But in physics, p equals mv, it is telling you a fundamental fact about the way things work. What is that? Momentum is the product of mass and velocity. So what this is telling you is that the product of mass and velocity is conserved, because momentum is conserved, obviously. Like if you consider a simple example, the momentum of the entire system is conserved. Suppose consider a truck car system. A car is stationary and a truck is moving with some speed. So since the car is stationary, the velocity of the car is zero. So the car's momentum is also zero, because mass times velocity is momentum. So velocity is zero and mass is of course non-zero. The car has mass. But the non-zero mass multiplied by a zero velocity, that will give you zero. But the truck is moving with some velocity, so its momentum will be, say, let's say the truck's momentum is 1,000, and you have to mention the units, otherwise it makes no sense. So it's 1,000 mass into velocity, so kg meter per second. So the total momentum of the truck car system is 1,000 plus zero, that's 1,000. Now suppose the truck hits the car. So when the truck hits the car, the truck faces an obstacle. The speed of the truck will decrease a bit, and the car, on being hit by the truck, the car will move forward slightly. So the car, for that moment, the velocity of the car will increase a bit. So the car will gain some momentum. It had some mass and the velocity will increase. So suppose the car's momentum is 200 meter per second, kg meter per second, and the truck's speed decreases, velocity decreases. So the truck's momentum will decrease. So in this case, the truck's momentum will be around 800 kg meter per second. So the total momentum of the truck car system is still 1,000. 800 plus 200, that's 1,000 kg meter per second. And the conservation of momentum can be easily derived from Newton's third law. Like if every action has an equal and opposite direction, like the action and reaction force, basically force equal if action equals minus f reaction. So from that you can easily derive the law of conservation of momentum. But what can you say just by looking at the equation p equals mv? From here you can say that for big mass, even a small velocity can produce a good amount of momentum that can be produced for a small mass with a huge velocity. Like suppose the momentum is supposed to 20. I'm not saying the unit here. So that can be achieved in many ways. Suppose you have a 20 kg object moving with a speed 1 meter per second. The momentum is 20. Obviously 20 times 1 is 20. So in this case, the object is like very massive. It is very heavy. Like it has a huge mass, 20 kg, but the velocity is small. Now consider a 1 kg object moving with 20 meter per second. In this case also the momentum is 20, the momentum is the same, but in this case the object's velocity is huge, like 20 meter per second, not huge, but still a good velocity. And the mass is tiny, just 1 kg. So this is what, from this, by looking at the equation, you can say that the mass and momentum, mass and velocity, are somewhat complementary. Like if this increases, the other has to increase, has to decrease if the momentum is to be kept constant. That's an obvious fact. That might seem like an obvious fact, but when you are first learning this at high school, you should, like, this is just, I'm trying to illustrate how to think of this. Okay. Like if you consider a more complicated equation, like let's say, give me a second. Suppose, okay, s equals ut plus half at square. So s is the distance and t is the time. So what does this tell you? Just by looking at the equation, okay, what does this tell you? So if I ask you to plot the distance time graph, it's going to be a parabola because it's proportional to t square, half at square. So this means the time is changing linearly, but with linear changing time, the distance might not change linearly, especially for over long periods of time, right? The distance might not change linearly. This is a conclusion you can draw just by looking at this equation. So you don't need this information just to solve a question based on this equation. Like if suppose the distance is given, the acceleration is given, and the initial velocity is given, then you can easily find the time, right? Just by putting the values in the equation and solving the equation. You don't need this information, but just by looking at the equation, you should ask yourself, what is this equation telling me? And it's telling you is this. The next conclusion you can draw is that for very short instances of time, If the time is very short, then t square will be an even shorter quantity. So so short that you can almost neglect the t square term. It will be almost zero. So in that case, s equals ut plus half ad square. Half ad square just ignore. So s equals ut. So in that case, there's a linear relation between the time and the distance. So s equals ut. So distance is speed u into time. That makes a lot of sense. And when you say half at squared, then again, that is also the same dimension. Now, acceleration means what? Velocity per time. So that's basically distance per time squared. So, and then we have into t squared. So t squared cancel. That is again the same velocity as distance. So obviously the same dimension as this. Obviously it has to be the same dimension. Otherwise you couldn't add these terms. But it just changes the nature of the graph. And then if you think of the Schrodinger equation, suppose just a simple, like just a rough example, maybe this example that might not make sense physically, but just a rough example. Suppose you see the Schrodinger equation, and then you are told that the wave function that the solution of the Schrodinger's equation, this wave function, this psi. Okay, so you suppose your teacher teaches you the Schrodinger equation, and you ask like, what is this psi? Then he says that it's called a wave function and it has no physical significance by itself. But if we square it means if we multiply psi with its complex conjugate, that's psi star, because psi is a complex quantity, and complex conjugate means replacing I, the imaginary number I, with minus I. Like, of course, any complex quantity will be of the form A plus IB. So psi times psi star, where psi star is a complex conjugate, the product of psi and its complex conjugate, that is what we say as psi square. So the interpretation is that the maximum interpretation, that this psi star, this psi square, the square of the wave function, that gives you the probability of finding the particle in a particular region of space. So this is the interpretation of the wave function. By itself, psi has no physical significance. So suppose you don't know this. You're told that psi square gives you the probability, but you don't know like what probability. Then just by looking at the equation, can you figure out like what probability? Of course you can. Like, what do I mean by what probability? Okay, so chi square can give, like, just consider the possibility. When I say probability, it could be that the probability that the particle is found at this instant of time. Of course, that sounds a bit strange and nonsensical, because the probability that the particle is found at this instant of time, that means the particle may or might not be found in other instants of time. That means the particle is sort of vanishing, like this moment it's here, the next moment it's not. Like, sounds crazy, but again, in quantum mechanics it's not so crazy. But let's not discuss that here. But it's possible. So what is Schrodinger's equation? It's that the Laplacian operator, that's nabla square psi. Or if you let me discuss it in one dimension and just the time dimension. I'm talking about the time dependent equation. So psi x comma t. Okay, so it's del square over del x square of psi plus 8 pi square m. Or let me discuss it like, let me use that form. Minus h square over 2m del square over del x square psi plus v psi, where v is the potential energy, equals to I h cut del t of psi. So del t of psi means the first order derivative, the first order time derivative of psi. And since psi is a variable of x and t, we are taking the partial derivative. And del x square of psi means the second order space derivative of psi, because x is the space coordinate. So here you see, probability should be a positive quantity, obviously, and that's why psi square, we're squaring it. Psi square gives the probability. Now here space is, this is just a rough intuition. Like, this is not a, just not a derivation or any rigorous proof or something, obviously. So here's the psi square, the del square, the psi, we're taking the second order derivative of the space coordinate, not the time coordinate. Like, and if we take the second order derivative of time coordinate, then this psi cannot be, cannot be interpreted as a wave, as a probability distribution in the first place, like as the square of which gives the probability in the first place. So from this, by just looking at the equation without knowing how it is derived and everything, you can make an educated guess that, okay, so maybe the psi is the probability that we find the particle in a particular region in space and not time. Yeah, like del square del x square of psi, and psi square is the probability. So just like that. So this is an example. So the thing is that you should always ask what the equation is telling you. Okay, that is, if you do that, then I think that will reveal you a lot about how the universe works, and that will grow your interest in physics. And like, that's definitely a reason that will give you that will give you one reason not to hate physics. And yeah, okay, so I'll discuss. Okay, so there are a few 2 to 3 points left to discuss in this video. So let me do that. I know this video, like anyway, it's a very pretty long video, so most of you will probably not watch it, and I don't blame you. Like it takes a lot of patience, but so anyway, I okay. So the next point is that, like, of course, physics is exciting. Like you are trying to understand the fundamental nature of reality, and that only physics can do. Biology, chemistry, they're all derived sciences, applied sciences. They can tell you how the immediate world around us works. But if you want to try to find out the ultimate secret of the universe, the most fundamental, deepest question, then you have to go to physics. And then we might ask, what, like, I might not be interested in that. Of course, you might not. Like, like, what is the point? Like, what if I don't try to understand the fundamental nature of reality? Then will I die? Or of course not. You can do what you can do. You're here, so all you have to do is survive. For that, you need money, and there are a lot of ways to earn money. Physics is not the only way. In fact, physics is not even a good way to earn money. Like most physicists are underpaid, especially in my country. So that's not a point. But the thing is that still, as humans, we are curious, and it might give you like some excitement, and to like when you think that, okay, so I'm trying to understand the fundamental nature of reality, right? So that's definitely one more reason not to hate physics. And so yeah, once you like grow the love for the subject, it's really not that difficult. Okay, so I usually hear this a lot, like physics is extremely difficult, and of course physics maybe is a bit difficult than the, it depends. Like for I personally find biology to be much more difficult than physics because I'm really bad at memorizing stuff. But for those who are bad with maths or calculations, they will find physics to be much more difficult than biology. I completely understand that. And then the thing is that, yeah, like uh, physics is really the search for the ultimate simplicity. Actually, not just physics. That's what science does. What is science basically? Science tries to find some regularity in the world, and then we just, do like we just try to build some laws, scientific laws or principles that will apply to a wide range of phenomena. So ultimately, we're trying to describe the world in a single theoretical framework. That's what science does, and make predictions based on that, and give and build innovative new technologies to make life a better place, and to make life better, to improve the quality of life, and so on. So, but the thing is that we haven't reached that level of simplicity yet, and so right now, and we know a lot about physics, and that is why physics seems tough. But fundamentally, physics is not tough. Physics is a fundamental science. It's about simplicity, and once you get an interest, and once just know the basics of physics, it's really not tough. Like now I'm doing an undergraduate course on physics, so I don't find it like, of course it's not easy, but I find it much easier than what I expected. And I'm now in my second year, so I really I did dealt with quite some topics which might seem difficult at first glance, like for instance legendary equation and best, like these special functions, and solving partial differential equations, deriving wave equations, and like I'm just discussing the theoretical parts. Like I'm skipping the computational physics portions, the new SciPy and new Python and all those stuff. Then we have done thermodynamics, of course, in much more detail than we do in high school. Like obviously, thermodynamic potential, like Clausius-Clapeyron equation, a bit of phase transitions, and kinetic theory of gases, which is a very like it's very important. And we will be doing statistical mechanics. We haven't done statistical mechanics yet. And then what else? Like we have done digital electronics, applied optics, were like not that difficult. But yeah, so we have done this kind of stuff. Or we have done optics, like ray optics, wave optics, and waves, and electromagnetism, mechanics, and of course mechanics at a much deeper level than we do in high school, obviously. So yeah, like the thing is that it's not really difficult once you get the basic intuition, and once you get interested, and once you know that the basic things. And if you study it a bit, you will automatically know it. It's nothing difficult. Like if you see it initially, you will feel overwhelmed and all. But if you just go with the flow, you will do it. Like obviously. But yeah, there, and yeah, of course, marks doesn't matter. Like marks does matter to extent, but you don't need to aim for full marks or some. That's not really not a good practice. Like uh, you just need to have good marks, but not the best one also. And Like I remember one of my art college professors. I can't name, of course, but the professor said that like she received not so good marks in her MSc on a particular topic, and compared to her, the average, the other students of her batch received good marks, but she was the only one from her batch who ended up pursuing PhD in that particular topic, and she did her PhD, and today she's quite a successful researcher and has published a lot of important stuff on that topic. So the thing is that if you are confident that I am interested in this and I can do this, and even if you get less marks, that doesn't mean that okay, so I got less marks, so maybe this is not for me, I cannot survive in this. It's not like that, because the exams judge you from one particular aspect, and you might not do well in one particular exam, but that's not a judgment of your knowledge and your eagerness to learn the subject, right? And one last example I'd like to discuss with you is that, okay, so you know this the point I'm emphasized over and over again in this video is that, like, whenever you're looking at an equation, try to understand what the equation is telling you, not just memorizing the equation and the meaning of the different symbols, and not that. Okay, so one example that comes to my mind is that in physics there is some, like, how is physics different from maths, by the way? Like physics is not just maths. Of course maths is very important in physics is nothing without maths, but in physics you're trying to understand the real world, and for that initially you need some intuition. You need the right intuition, and like there is no really methodical or mathematical way to get the right intuition. Like, okay, then everyone could have done it, then there wouldn't be scientists. Like everyone could have done it, then there wouldn't be geniuses. Like, so you develop the intuition based on your years of thinking and years of experience, and by observing nature, by observing the phenomena. Okay, and yeah, once you have the intuition, now to develop a theory out of it, to develop a quantitative theory, you need mathematics. Obviously that's where mathematics comes in. But first you need to develop the intuition. That's an important thing in physics. And an incident that comes to my mind is that a few years ago, when I was like our that pressure, hydrostatic pressure is just the constant atmospheric pressure plus h rho g. So basically it's just h rho g. We are assuming the constant atmospheric pressure to be zero. Like, take it to be zero with some reference frame anyway, just to make it simple. Otherwise you can take that also, doesn't matter. So pressure is h rho g. H is the height, h rho g is the pressure at a depth h in a fluid system. Like suppose say you have a beaker of water, and at a depth h under the water, like h is the depth of the, suppose you want to find the pressure at a point inside the water, and that point is at a distance h from the top surface of the water. So at that point, the pressure is h rho g, where g is the acceleration due to gravity, which is more or less the same on Earth. And uh, like g varies very slowly with distance. And for a beaker of water, the g is almost same for all the for suppose you have two beakers of water kept side by side, g will be almost the same, and h is the height and rho is the density of the water. Okay, so h rho g gives you the pressure. Like obviously pressure is force times force per area, and you can just derive h rho g, but if you just put the usual equations for force and area, like force is mg, that's a gravitational force, and area, you just put the area. Like, I'll leave that to you. That's a pretty short derivation anyway, just a high school physics. So anyway, it's h rho g. Now the thing is that, suppose just a second, just give me a second, let me share my screen. Okay, I just want to show you this, just a second. Okay. Yeah, then just a second. All right, let me just, I think I can do it with a whiteboard. Okay, yeah. I've not used this whiteboard before, this Zoom whiteboard, but I hope this will be enough. Okay, so okay, I guess you can see this, right? So basically, I draw a container of this shape, and then I draw a container of this shape. Oh my God, just a second. Okay, where is that? Okay, yeah. Yeah, I think this will do. So both of them are filled with some fluid, say water or whatever. And suppose this is my point A and this is my point B. and both of them are at the same height, like I'm drawing this at the same height from the top surface of the water. So now this is A. Okay, I'm just writing A, and this is B. Yeah, okay. All right. So the pressure at point A and point B should be the same. Because I've already said that the height from the top surface of this fluid to A, I mean this line I've drawn here, this height is H and this height is also H, and G will be the same for both the speakers obviously. And uh, assume that they both of them are filled with the same fluid, so the same density. So H rho G, all the three terms are constant. So PA, or the pressure at A, will be the same as PB, or the pressure at B. So if you apply the equation P equals H rho G, you can immediately see that A is pressure at A is equal to pressure at B. But if you try to think of this intuitively, then some people might initially have this misconception that, suppose if you think about A, like the pressure at A, so you look at this volume of water above A. Okay, so it's a huge, like compared to B, like there's a huge volume of water above A, since the shape of the container is like this, right, like a V. But if you see B, in the second case, if you see B, the volume of water above B is less because it's an inverted V. It's an A shape. Okay, so the volume of water is less. So it might seem that since there's more volume of water above A, that might exert a greater pressure on A. So the pressure at A must be greater than the pressure at B. So intuitively, it seems that PA is greater than PB, but the equation tells you PA is equal to PB. So this is this question the teacher asked, and then the teacher explained the answer. And then one student said that, so in physics, equations are to be trusted, intuitions are not to be trusted, because by intuitively it seems that PA is greater than PB, and but the equation is giving you the correct result. So here I would say that this is not a right conclusion, because the thing is that, okay, equations, like intuitions are, from this you cannot conclude that intuitions are not to be trusted. What this proves is that you should train your mind to have the right intuition, because thinking about this entire column of this entire volume of water above A and B, this was the wrong intuition in the first place. So if you have a wrong intuition, then obviously you're going to get the wrong result. The correct intuition in this case would be, let me just choose this thicker line. Okay, thicker pencil. Okay, so now the correct intuition is that see, we are considering the point A. We are not considering some area. Like we have not set the pressure over this area. Okay, we are considering a point. A is a point and B is also a point. So to find out the pressure on this point, we have to consider the water just strictly above this point. So that is this cylindrical column of water, like not even cylindrical. It's a cylinder of radius 0, basically. Just this line of water above A. So if you consider this and the same for B, then we immediately see that they are the same height and they're almost like just like a line. So it doesn't matter. So if we think of it like this, then we immediately see that this is the same in both the cases. So intuitively also we can say that PA is equal to PB. So the right intuition in this case was that you have to identify that A and B are points. So we should look at the column of water just above this point A and B. Looking at the volume was the wrong intuition. Yeah, by looking at that, basically what happened in this case is that since these containers are differently shaped, our brains probably thought that maybe this question, it has something to do with the shape. So we assume that, okay, so this shape is like this, so maybe it's a greater volume of water, so maybe PA will be greater than PB. So yeah, intuitions in physics are to be trusted, but yeah, you should develop, like you should have the right intuitions. That's what I'm trying to say. Okay, that's what I'm trying to say. So that's what I'm saying, that like you just just a second. Okay, so you just try to learn physics intuitively, not just, of course you have to memorize the equations, you have to know the derivation of the equations, and but you just ask yourself, what is this equation telling me, and you're just trying to learn physics intuitively. Okay, that helps. I mean, at least if you're trying to develop a love for physics, or at least if you're trying to find out why not to hate physics, then that helps. I believe that helps. And the last point is that a lot of people ask me, like, a lot of people, sorry, excuse me, a lot of people ask me, like, okay, so I love physics, I want to do research in physics, but can you give me some advice? Like, of course, I'm not a researcher, I'm not qualified to give advice, but I would like to tell you something anyway from what I have learned and from I just want to share my perspective with you. So if you're looking for money and if you're looking for an illustrious career, then obviously researcher or physics researcher or academic is probably not for you. But if you have decided that no, I want to research physics, I want to find out like I have to. If you've chosen physics and if you're determined about a choice, then very good. Then I would say that the best advice is that there is an article called Four Golden Rules. That article is written by, that Professor Steven Weinberg. He's one of my favorite physicists. He passed away a few years ago, about 2 years ago. He's one of my favorite. He's one of my favorite physicists. I read his book, Dreams of a Final Theory, and he was a great physicist. Obviously, he was a Nobel laureate. Then he developed quantum electrodynamics and the electroweak, not electrodynamics. He developed the electroweak theory. He unified the weak nuclear force with electromagnetic force. And yeah, so anyway, the point is that in his article, the Four Golden Rules, he says, like, he discusses four rules, important rules that should be followed if you really want to, like, four good advice to be followed. If four good advice he has for aspiring physics researchers. So they are just I just noted them down somewhere. Let me just give me 1 second. Give the link of the article in the description. Please do check it out. Like it's extremely important, like especially if you're an aspiring physics researcher, or even just an aspiring researcher, not even physics researcher, aspiring scientific researcher. Like you really, you really should read this article. So yeah, let me just, it's a very pretty short read. Let me just read it out for you, but then I'll end this video. When this is Steven Weinberg saying, when I received my undergraduate degree about 100 years ago, the physics literature seemed to me a vast, unexplored ocean, every part of which I had to chart before beginning any research of my own. So first of all, there is this a misconception that before I can do research, I have to know everything that is known about the subject. That is not true. You have to know the basics, the main history of the subject and the basic things. At least you have to know the basics about the field of which you're trying to research. Like not the entire of physics. Like suppose you're researching, suppose let's say solid state physics, so you should have a knowledge in that field. But it's not possible, and it's if you say that before I start my own research, I should know everything that is known, then that's not possible. Then you will basically spend your whole life knowing everything and you will never do research. So the first important advice that Weinberg gives you, and that's very good advice. I give you the same advice. You just you just develop an important hypothesis, an important research question, and you start working on it. And uh, while working on it, you will feel that okay, I need to have more knowledge about that. So then you just learn about that on the go. Okay, that's it. So how could I do anything without knowing everything that had already been done? Fortunately, in my first year of graduate school, I had the good luck to fall into the hands of senior physicists who insisted over my anxious objections that I must start doing research, and I pick up what I needed to know as I went along. Otherwise, if you wait for the time that you become perfect to do research, then basically you will wait for your whole life. So you must take the first step as soon as possible, as early as possible. So it was sink or swim. To my surprise, I found that this works. I managed to get a quick PhD, though when I got it, I knew almost nothing about physics. But I did learn one big thing, that no one knows everything. I do not have to. The second rule, this is the first rule. The second golden rule is that another lesson to be learned to continue using my oceanographic metaphor is that while you are swimming and not sinking, you should aim for rough water. Like, yeah, while you are sinking, that means your first priority should be to get yourself afloat, to learn the basics of swimming and the safety equipment, this life jacket and whatever. But when you are more or less, when your life is stable, like when you're swimming and not sinking, then you should aim for rough water. You should always take risks. Like when I was teaching at the MIT in the late 1960s, a student told me that he wanted to go into general relativity rather than particle physics, the area Weinberg was like I was working on. This is Weinberg speaking. Because according to the student, the principles of the general relativity were well known. General relativity is a mathematically well defined theory, while particle physics was a rather new theory and it was like a mess. So, but it struck me that he had just given a perfectly good reason for doing the opposite. Like particle physics was an area where the work was going on, where the creative work was going on, where the creative work could still be done. So it really was a mess in the 1960s. But since that time, the work of many theoretical and experimental physicists has been able to sort it out and put everything, like almost everything, together into a beautiful theory known as the Standard Model. So my advice is to go for the messes. That's where the action is. If you if you go for the well-defined theory, then already it's well-defined. There's nothing much you can do. If you want to try to do something new, then go for the rougher areas. Like that's what he's saying. And that's obviously definitely that's a very good advice. But of course, I have to choose it wisely. Like, for instance, nowadays choosing to research on LQG or string theory might not be a very good decision, because those fields are almost stalled, and researching those will maybe not give you much good chance of getting a postdoc or a PhD position. But the thing is that still you should work on the new areas on physics, the rather new areas where the work is going on, like complexity science and everything, rather than old areas like GR. But yeah, maybe GR, there are a lot of things to do about with GR right now. Like recently there is a lot of research going on about gravitational waves anyway. So yeah, just the advice. Okay. The third piece of advice is probably the hardest to take. And this is probably, in my opinion, this is the most important, because I myself fail to follow this advice at times, but I realize that it's true. I realize that it's very important. This is that it is to forgive yourself for wasting time. Like, students are only asked to solve problems that the professors know to be solvable, of course. And in addition, it doesn't matter if the problems are scientifically important. They have to be solved to pass the course. But in the real world, like when you're researching, it's very hard to know which problems are important, because you don't know. Research means you don't know anything. You have to figure out the question by yourself, and you have to search for the answer by yourself. Like ideally, that's what research is, right? So in the real world, it's very hard to know which problems are important, and you never know whether at a given moment in history a problem is solvable. Maybe it seems to you that it's probably important, but suppose it led you nowhere. So you wasted years of efforts and research on it, but then you reach nowhere. Then you feel like, obviously you feel down and hopeless. Like, but the thing is that it happens. Like, it's not like you will not win every time. It's okay to waste time in research. At the beginning of the 20th century, several leading physicists, including Lorentz and Abraham, were trying to work out a theory of the electron, like partly in order to understand why all attempts to detect effects of Earth's motion through the ether had failed. But then we had the Michelson-Morley experiment. There was no ether, then Einstein's special relativity, and so on. So we now know that they were working on the wrong problem. At that time, no one could have developed a successful theory of the electron, because quantum mechanics had not yet been discovered. And it took the genius of Einstein in 1905 to realize that the right problem on which to work was the effect of motion on measurements of space and time. And this led him to the special relativity, theory of relativity, as he will never be sure which are the right problems to work on. There is no methodical way to understand which are the right problems to work on. Like I was saying, there is a bit of intuition in physics. Like, once you have the right intuition, then you can develop your theory mathematically, but there is a bit of intuition, right? So as you will never be sure which are the right problems to work on, most of the time that you spend in the laboratory or at your desk will be wasted. If you want to be creative, then you will have to get used to wasting time, spending most of your time not being creative. If you want to be creative, then you will have to get used to spending most of your time not being creative, to being becalmed on the ocean of scientific knowledge. Very important advice, this one. Okay. Like, yeah, it's okay to waste time. It's not possible to be creative like all the time, and you have to accept that. And yeah, I think like it's not like, even if you do some start some research and find out like you don't reach any significant conclusion, or it fails, that doesn't mean like, it's like it said, you did not fail. You just showed that this path was not the correct path to take. So you helped the future generation of scientists in some way. So and think of it like that if it comforts you. Finally, learn something about the history of science. The last example. Yeah, this is also a very good advice. Learn something about the history of the science, or at the minimum, the history of your own branch of science. The least important reason for this is that the history may actually be of some use to you in your own scientific work. It might be of some use to you, but that's not the most important. That's in fact the least important reason, according to Winberg. For instance, like now and then scientists are hampered by believing one of the oversimplified models of science that have been proposed by philosophers from Francis Bacon to Thomas Kuhn and Karl Popper. So the best antidote to the philosophy of science is the knowledge of the history of science. Now, Winberg is obviously a strong like critic of philosophy of science, and yeah, like philosophy. I'm not a critic of philosophy of science, but I am myself and also a critic of philosophy, especially the use of philosophy in science. But anyway, okay, so the most important reason for learning about the history of science is that, most importantly, the history of science can make your work seem more worthwhile to you. And it's important, like we're all humans, and if my work seems worthwhile to me, then I will automatically get more energy to do the work, more encouragement to do the work. And learning about the history of science will make my work seem more worthwhile to me. Why? Because see, as a scientist, you're probably not going to get rich. Your friends and relatives probably won't understand what you're doing. And if you work in a field like elementary particle physics, you won't even have the satisfaction of doing something that is immediately useful. Like maybe you're working in semiconductor physics, you develop a room temperature semiconductor that's immediately useful. There's a lot of application that will revolutionize the electronics industry. But if you're working on elementary particle physics, maybe you will develop some theoretical discovery, but that's not immediately useful, right? So you won't even have the satisfaction of doing something that's immediately useful if you are work in a field like elementary particle physics. But you can get great satisfaction by recognizing that your work in science is a part of history. Like you're making history, kind of. Look back 100 years to 1903. How important is it now that who was Prime Minister of Great Britain in 1903 or President of the United States? What stands out as really important is that at McGill University, Ernest Rutherford and Frederick Soddy were working out the nature of radioactivity. This work, of course, had practical applications, but much more important were its cultural implications. The understanding of radioactivity allowed physicists to explain how the sun and Earth's cores could still be hot after millions of years, nuclear fusion. In this way, it removed the last scientific objection to what many geologists and paleontologists thought was the great age of the Earth and the sun. After this, Christians and Jews either had to give up belief in the literal truth of the Bible or resign themselves to intellectual irrelevance. This was just one step in a sequence of steps from Galileo through Newton and Darwin to the present that, time after time, has weakened the hold of religious dogmatism. Reading any newspaper nowadays is enough to show you that this work is not yet complete. There is still a lot of religious nonsense going on. But yeah, it's civilizing work of which scientists are able to feel proud of. So yeah, this was very important. Winberg's 4 golden lessons. And I think that's all for this video. I don't want to make it any longer. So yeah, that's all about how not to hate physics. Any comments, anything you'd like to discuss, the comment section are open. I'd be more than happy to read your comments. Thank you, guys.